Okay. Welcome to Math 150, Section 2, Lecture 7. There were some technical issues with the recording for Class 1 today, so I'm almost surely only going to post this one. So today we're going to talk a little bit about level sets. We'll talk a little bit about spherical and cylindrical coordinates. We will talk a little bit about how you can use Mathematica to do a lot of these calculations. And then if there's time at the end, we'll talk a little bit about whatever other problems you want to discuss. So there are some questions to talk about level sets. And so the way to view a level set is it is all points that evaluate to the same value by the function. So you've seen stuff like this before. What is an isotherm? For my chemists or physicists. Or just somebody who cares about the weather. So an isotherm would be what?
Isn't it the contour line?
It's the contour line. It's the places where you have the same temperature. What's an isobar?
Pressure.
Pressure, not drinking is fume. Okay. What's an isodoohickey? It's where the doohickey is from. Iso means equal, and so you often see plots like this. And so the advantage of these plots is it allows you to present three-dimensional information in a more compact way. So we'll talk a little bit today about how you present information. The level set is trying to give you a nice way to quickly look at what's going on. You sometimes might see these as maps of elevation. That's the standard way to think of a level set. And you just have a nice flat plane, and it tells you here's like the mountain. You can see these are all the points at 1,000 feet, 1,500 feet, 1,700 feet. You can see the mountain climbing. So let's take the function f of xy is x squared minus y squared. And so we want to find the level sets. So we want to find all xy such that x squared minus y squared equals c. So the first question is, no matter what value of c I give you, will you always be able to find an x and a y such that x squared minus y squared equals c? Or will there be some c that have no x and y that work? What do you think might be the easiest choice of c? 0. So if c equals 0, then you have x squared equals y squared. What if c is positive? Can you give me a pair x and y that would work for positive choice of c? I'm saying c is just some positive. No, c is an arbitrary positive number.
So x is up to 0.
I'm sorry? So x squared would have to be greater than y. So if I give you a positive c, will there always be a choice of x and y that works? So give me the simplest choice for positive value of c that will work. I haven't told you what c is. So all I told you is c is positive. You have to give me an x and a y that work. So I want x squared minus y squared equals c. And c is positive. What could you choose? What if you had x squared minus y squared equals 4? Give me a point that works. Two comma 0. X squared minus y squared equals 9. Give me a point that works. 3 comma 0. Now you have c. Give me a point that works for x squared minus y squared equals c, where c is a positive number. Not c squared. Square root of c, comma 0. So if c is positive, just take y to be 0, and it's no trouble at all. What if c is negative? What if c is negative 4? What would you take? 0, 0, 2, or 0, negative 2. Either one would work. So if c is negative, we just do something very similar. So this will be interesting. The level set will always be non-empty for this. And I know that before I do any calculation. For a lot of things we've seen here, it doesn't really matter. You can rotate. It only depends on x squared plus y squared. Will this value change if I flip x and y? if I rotate them? Does this depend more than just how far x and y is from the origin? Does it also depend on where they are? Does it depend on the angle? So when you look at this, is it just a function of x squared plus y squared? So if it's just a function of x squared plus y squared, then, whenever I put an r cosine theta and r sine theta, I should get the same value no matter what theta I put in. So if I put that in here, I'll get r squared cosine squared theta minus r squared sine squared theta. So that's r squared cosine squared theta minus sine squared theta. Or r squared cosine squared theta, if you happen to remember your angle function. This depends on the angle greatly. And if you look at it, it doesn't depend on just x squared plus y squared. It depends on x squared minus y squared. So I don't expect this to be independent of how I rotate about the origin. If I flip the roles of x and y, what do I do to the value of the function? So if I switch the roles of x and y, so instead of doing 3, 4, if I look at 4, 3, what happens to the value? You negate it. So I do have some symmetry. So if I know what's going on at x, y, the negative of that is happening at y, x. So I have some information. So let's try to solve for the level set. The easiest is c equals 0. So if c equals 0, you get x squared minus y squared equals 0. That means x equals plus minus y. And it's just going to be 2 45 angle lines. If c is greater than 0, then we have x squared minus y squared. And I'll write it as the square root of c squared. Because I recognize what's going on the left-hand side. If I just divide, this is x over the square root of c squared minus y divided by square root of c squared equals 1. What is this the equation of? A hyperbola. And so this will be a hyperbola like this. If c is less than 0, I'll leave that to you. It's going to be a very similar calculation, but it'll be a hyperbola going in the other direction. And these hyperbolas will all be fitting in here. So if you really want, you'll be looking at something like this. So this is how we would analyze a problem like this. Now, one of the advantages of being at the blackboard is I can modify this very quickly. Instead of x squared minus y squared, what would you rather have? So what would have been easier to study? What would have been more familiar to study? Instead of x squared minus y squared, plus. So we can just do a quick search and replace with a plus. And see what does that do. So now, things become a little bit more interesting. When you have x squared plus y squared equals 0, what is the only solution to that? 0, 0. So the level set is just a point 0, 0. If c is greater than 0, we have a circle of radius squared of c. What if c is less than 0? Can x squared plus y squared be negative? No. So no solution. The level set is empty. As an aside, if I do some kind of strange change of variables with I equals the square root of -1, this is a little bit strange to do because x and y are real numbers. But then negative y squared, if I change it like this, becomes a positive y squared. And there is a way to basically change variables and have the hyperbola become a circle or an ellipse. We're not going to go into that, but just pointing out that formally, if you do a strange change of variables like this, you can make these curves come together. Now let's do another example. Let's say for you, f of xy is x squared plus y squared minus 6x plus 4y plus 7. All this 7 does is it just takes everything and moves it up and down. It just changes the value of the function by 7. So really, this has no significant impact on figuring out what the level set is. The meat is coming from everything else. If you didn't have the negative 6x and the 4y, what shape would it be? So if you just had x squared plus y squared plus 7, what kind of shape would that be? Circle. So we've got this annoying factors of the negative 6x and the 4y. Maybe we can figure out what they do. Maybe there's a better way of writing this. How would you group the terms? Is this how you would want to group them? Right, what would you group them?
The x and y.
Let's put the x and the y together. Here, x squared minus 6x plus y squared plus 4y plus 7. So almost surely, there is a reason there are large blank spaces there. I can't pretend to be surprised because this is the second time I'm giving the lecture today. Does y squared plus 4y, does that look close to anything you know? What does that look like? Yeah. So if I add 4 and subtract 4, I have done one of the most common important things in mathematics. Nothing. I've done nothing in a good way to make the algebra nicer. And this will now give me y plus 2 squared. What should we do with x squared minus 6x? Plus 9 minus 1. Which order? Yes. Plus 9 minus 9. And now, this part over here is just going to give us x minus 3 squared. So we have a minus 9, a plus, and the minus 4 is minus 13, plus 7 is minus 6. And now we can see this looks a lot like a circle. So if you want to solve f of xy equals c, that's the same as this whole thing equals c. So that's the same as x minus 3 squared plus y plus 2 squared equals c plus 6 square root squared. So I'm just writing it as, square root squared, so you can easily see what the radius is. I bring the 6 over to the other side, and what I'm left with is, oh, okay. So as long as x minus 3 squared plus y plus 2 squared is constant, I'm in a level set. If I wanted to figure out what is the value of the level set, I would then plug that back into here, into the function. We have to remember that, the value of the function would be what x minus 3 squared plus y plus 2 squared is, and then subtract 6 from that. Okay? What is the smallest value f of xy can take on? So what's the smallest value it will take on? Negative 6. So it'll take on negative 6 when x equals 3 and y equals negative 2. So if you look at this over here, if I take C equals -6, yes, square root of 0, not a problem. So if C is greater than or equal to -6, you have a circle centered at 3, -2 of radius square root of C plus 6. And what happens if C is less than -6? Is that?
It's like not defined.
So it's not that it's undefined. What's the level set? It does exist.
Oh.
It's empty. It turns out there's only one set we know exists. It is the empty set, the set with no elements. And there's a way to define all of the integers starting with the empty set. So just in terms of language, it exists, it just doesn't have any elements. So the level set would be empty. Okay. So what I want to do now is I want to convert this to showing some plots. All right, so what I want to do is I want to talk a little bit about how to glean information from plots. And that's a lot of what we're doing, is we're trying to find good ways to write what we're doing so you can clearly see what is happening. And you can see how well the transcription is doing. This is a plot of sunrise and sunset in the nearest metropolis to Williamstown, the great city of North Ave. Okay? Which one do you think is sunrise? Which one do you think is sunset? Which time of day do you think is the sunrise time? Which is the sunset?
Sunrise on the bottom.
Sunrise on the bottom, sunset on the top. If you notice, the change in sunrise from day to day is not that severe, except twice, when you have this massive change. What's going on? Daylight savings. About how long is daylight savings? Well, it's about an hour. And you can see when you're looking at this plot very quickly that there are 2 points in the year when something interesting has happened. Does this mean that there is something strange happening to the orbit of the Earth or the Sun? No, it might be. It means these are 2 points that are worth investigating. It does not mean that something nefarious is happening. It doesn't mean something strange is happening in terms of the physics, but something is happening at those points. There could be a reasonable explanation. It's just saying these are points to look at. Okay. I want to show another plot. This is from a few years ago. This was who America was rooting in the Super Bowl, Patriots against Rams. If I'm drawing a Ram, does that mean we want the Rams to win? What is another way of saying something very similar? Right, so just because it's a Ram does not mean you're rooting for the Rams to win. It could be, oh God, I gotta choose one of the two. You know, it's the lesser of two evils. I'll choose the Rams. So, excellent. So there are a couple of places on this map that are interesting. One place is Louisiana. What else is interesting? And the other part, I mean, it's basically a sea of Rams. Any other places that are not Rams? Yeah, anybody know what part of the country that is? New England. So it's not too surprising that New England is rooting for the New England Patriots. You do not need to be, oh, I do realize this is being recorded. It is amazing who can be commentators at professional sports games. I remember the very first time the Carolina Panthers were in the Super Bowl, they were talking about how they were unique among all franchises in North American sports. As not named after a city, not named after a state, but the Carolina Panthers were named after a region of the country, the Carolinas. And isn't that amazing? There's no other place like that. Anybody know who the Carolina Panthers were playing in their first Super Bowl appearance? The New England Patriots, yes. And I'm just listening as they're going on and on and on about how fascinating the name is. And we go, you do realize they're playing the Patriots. So, is there a natural explanation for why New England is rooting for New England? Yes. Why is Louisiana rooting for New England? You need to know a little bit of your football history.
Bad call.
There was, no, bad call doesn't even begin to describe it. It was so atrocious in the NFC Conference Championship between the Rams and the New Orleans Saints that the NFL issued an apology, where basically it was late in the fourth quarter. If the Rams make one more first down, they can essentially run out the clock and win. And so one of the defenders on the Saints can run the game out. So one of the defenders on the Rams says, well, I got nothing else to lose, and just does an incredibly illegal hit, which was missed. And it should have been an automatic first down. The people in New Orleans and Louisiana were furious. One of my friends who serves in the Phi Beta Kappa Senate with me was very kind. He's telling me, the papers and the headlines from New Orleans, just how they viewed this. When the Super Bowl happened, they actually played in a lot of bars, not the Super Bowl, but a previous Super Bowl when the New Orleans Saints were playing. They were furious at the call. So in this case, when you look at the sea of rims, something is happening here. And this tells you, okay, this might be a good place to investigate with finite resources. Any other place on the map that might draw your attention? There is one other place. Can you see it now? I'm sorry? Little dot. Anybody know where that is? St. Louis. Anybody know why St. Louis might be rooting either for the Patriots or more likely against the Rams? The Rams left St. Louis and moved to Los Angeles. And so when you look at a map like this, most of the map, nothing is happening. But there's three places that look very different, and they draw your attention. These might be places that are worth investigating. It could be nothing strange is happening. Okay, and so it turns out for two of them, there were really interesting stories as to why they had different behavior. What I want to do now is continue talking about how to view things, and I'm going to shift to some code I wrote earlier in the first class. So in Mathematica, when you use an underscore, this is how you define a function, and what is underscored are going to be your variables. Now, these functions are not that bad, but if I want to use them a couple of times throughout the notebook, it's better to just define them once and then have the name and have them available. I could, of course, define this to be f, and the next one I could also say to be f, but if I do that, I would then overwrite this definition here, and this way I can work with both of them. So, anybody recognize f and g? Where have we seen them before? 10 minutes ago. Right? These are the functions we were looking for the level sets. And so the first thing is I'm going to do a three-dimensional plot. I'm going to plot the function f of x. X goes from -5 to 5, y goes from -5 to 5. And when I do that, I get the plot here. And what's nice is I can zoom in, I can rotate it a little bit, see how it looks. And you can see there's some kind of symmetry between flipping x and y and maybe negation in terms of how the sheet goes. To find a level set, I want to find all the points that have the same height. How can I do that? Well, here I had my range and I had the function I was plotting. I now have curly braces, and I'm now going to plot multiple functions. I'm going to plot the function c and f of x in the first, and then c and g of x in the second. And because I use the manipulate, that allows me to change the value. And so in Mathematica, it's shift enter to compile lines, so I'll hit shift enter. And then down over here, you can see here's my value of c. C is starting off at -5, and you can see how it's hitting. And if I look straight down, you can see, oh, there's my hyperbola. If I change it from -5 to +5, it should be the hyperbola is going in the other direction. And you see it's going in the other direction now. What's another good, interesting choice of C to take? We did -5, we did 5, would be another good choice. 0. Anything else is essentially just rescaling. If I do -2, it's similar to -5. If I do +2, it's similar to +1. 0, oh, that's interesting. And there's the straight lines. There's the degenerate hyperbola becoming, two intersecting lines. What if I do 0.01? Can you tell that those are no longer straight lines? I'm sorry? I can't. If I do 0.1, and now I can see, oh yeah, I saw that they moved up a little bit over there. So they're clearly no longer straight lines, but the rest looks pretty straight over here. I'm not really seeing that much of the curvature. No, I mean, at that point, they are extremely close to straight lines when C is that small. I would have to go very far out to start to see the differences. I can pick this up and play the games and rotate it. Now, another way to do stuff like this is to do contour plots. This is just the other one. This is the function g, the more involved one. And you can see, oh, there is our circle. And it is possible for a circle not to be centered at the origin. You normally don't see that in our books. It's circled down here. If I start to increase C a little bit, the level set gets larger. And eventually, you'll see becomes so large, it's falling outside of the region I was choosing to plot. And what this is saying is, look, choosing to plot in a box -555, -555, centered at the origin is kind of stupid when the action is happening at the point 3, -2. All right. Last item is contour plots. So Mathematica has a nice function that allows you to do a contour plot. And here, I have the range that I'm doing. And what you can do when you have a contour plot is you just put your cursor on one of these lines and you see the value. And we can see it gets larger and larger and larger as we go further out. Over here, on this circle, it's going to be 0. It's sadly not doing enough detail to show what's going on at the center, which the value should be -6. If you remember what we had before. So if I change all the 5s to 0.5, oh, that won't work because it's not centered. Instead of looking at the function g, I could look at the function f. That was the hyperbola. And now you can see the straight lines. And if you put your cursor over that, you can see it has a value of 0. Here, it's going to be 5, 10, 15, 20. And over here, -5, -10, etc. And you can see that basically if you rotate it 90 degrees, rather than going up, you now go down. And the idea is a picture like this is supposed to allow you to quickly look at what's going on and get a sense of the action. How many of you have seen The Matrix, the original movie? A couple of the first parts. So there's a great line of code of script when I think Cypher is talking about looking at the code in real time, and he can now just translate it and just in his mind see the people and not the code. If you do any programming language, if you look at things enough times, you can actually just translate directly. When I see a map like this, I can say, okay, it's rising in these directions symmetrically, it's falling in these directions symmetrically. And that's the whole point of something like this, is to be able to very quickly see what is happening. Okay. So I will turn it back. And so what I want to do now is a little bit on spherical and cylindrical coordinates. So the extra credit problem is a really good one to discuss, as it highlights how to do a complicated problem that is at least worth doing. How many of you have ever had a painful derivative to calculate? It's almost a requirement when you take a calculus class. Let's see if you can do this. And they'll give you a chain rule embedded in the product rule and all these things. Do they ever tell you what that function of I? No, this is just a test to make sure you understand what you're doing. You might have had the exponential of an exponential. There are a couple of problems in mathematics where the exponential of an exponential aligns, and it's fascinating when you have degrees like that. So what I want to do is the extra credit problem, because it's actually not an unreasonable. It's something that could very physically happen. We have a sphere of radius 2. And then we have a cylinder of radius 1. And the idea is we remove that cylinder from the sphere, and we look at all the points that are left. There are 3 natural choices for coordinates: Cartesian, and what else? Cylindrical, and what else? I'm sorry? Not polar. Cylindrical trumps polar here, because you have 3 dimensions. And spherical. Why is the cylindrical coordinate a good choice for this problem? You have a cylinder, right? It's not subtle. Why is spherical a good choice for this problem? You have a sphere. Okay, it is really hard for you to disguise when to use some of these, right? Whenever you see things like x squared plus y squared plus z squared, you should think spherical. When you see x squared plus y squared, you should think polar or cylindrical. So as a rule of thumb, it's nice to have a bunch of things to try. As you get better, you start to be able to quickly look at things and see which things to try in which order. This might remind you of integration techniques. You have a lot of different ways you can try to do an integral. Let me try this, let me try this, let me try this. Eventually you find one that works, hopefully. And the more experience you have, the faster you are. Okay, so now we want to try to figure out what's going on. Let's do cylindrical first. There are 2 ways to do cylindrical. One of the variables in cylindrical is going to be very easy to understand. Is it R, is it Z, or is it beta? Why R? But you have to figure out which values of R, theta, and Z will work. And so if I look at this, I don't think R is, you just want to just quickly look at it and know what's going on. I'm sorry? Yes, why would theta be the easiest one to look at here? Yes, you can just keep walking around, right? There's complete symmetry in theta. So we know for this, zero less equal to theta, less equal to 2 pi. Because if you have a point, you can just spin it around. So the challenge is going to be figuring out what R and figuring out what Z is. So we can either have Z range and then determine R, or we can have R range and determine Z. I'm going to first have Z range. If we think about this, you can see that there's going to be a maximum height for Z. And there'll be a minimum height. If you go too high, it's not going to work. So this is 1 unit. This is 2. I'm going to call that angle P naught. Let me just expand this out. Now I'll call that Z naught for the largest value of Z that I can see. Yes. C naught. Because we use phi, I know we're using three components, but we use phi to talk about the angle coming down from the Z axis. So I want to keep theta from rotating in the XY plane. So let's call that C naught. Anybody know what value Z naught is going to be in this triangle? This is a famous triangle. What is it? What would Z naught be? Not radical 5. The hypotenuse is 2. One of the sides is 1. What's the other side? Square root of 3. So 1 squared plus z0 squared is 2 squared. So z0 is square root of 3. And then you can ask, well, what is the angle that corresponds to the square root of 3? This should be pi over 3. And for some of you, I might have emailed pi over 3 by mistake, so I apologize. If not, I don't apologize. So we know that angle is pi over 6. So the largest we can do is square root of 3. What's the smallest we can do? Negative square root of 3. So negative root of 3 is what's equal to z, what's equal to square root. So live somewhere in there. Now we just have to figure out what value of r is acceptable. So if I give you a value of z, then any r from here to here works. And remember, r is the distance, parallel above the xy plane. Let's try to figure out what's going on. So here, here is 1 unit, right? And if I do that, I'm doing something like this. What I want to do now is not tell you what that power is, but tell you that I've gone up these units. Okay? And so I go up z units, and then I start over here, and go all the way over. So how much would that length be? How much would this length be? That's just going to be 1. Right? I choose a value of z. I start here at 1. So we know that r is going to be at least 1.
I'm sorry, what is one?
This length over here from the z-axis
Oh,
to where we hit the cylinder. If I tell you this is z, then the minimum over here is going to be 1. We know 1 is what's equal to r. I really want to know how far can you go? You can go all the way until we hit the boundary of the sphere. So again, once I pick the height, I start off at 1 unit and I go until I hit the boundary of the sphere. Well, I now draw my triangle like this. And what is this hypotenuse going to be? What is it? It's 2. We have a sphere of radius 2, so this is going to be 2. It's terrible that we have z's and 2's in the squaring thing. This whole thing, this is 1 minus r. This whole thing is going to be the r maximum that we can do. So z squared plus r squared is 2 squared. So the biggest r is going to be 4 minus z squared. And take the square root. Yes.
I thought the line.
This is a cylinder. We throw away a cylinder of radius 1. So that means wherever you choose a height for z, the very first value of r that can happen is r equals 1. If I was looking when you're inside the cylinder. So I'm walking in this direction. I'm starting at some height and I'm walking to the right. And then I just spin myself.
You like drew it upside down.
I'm sorry?
Like I drew mine like the other kind of triangle, so I was just
Well, you might get that triangle in the moment when we do it the other way. So I'm doing first specify z and then r happens. You can also specify r and then z. And so when we specify z, we start off at 1 and we keep walking until we hit the boundary. So what is the largest r that we can take? It's square root of 4 minus z squared. And so this is going to be one way to write it in cylindrical form. The other way is 0 plus equal to theta plus equal to 2 pi. We could specify r first. Well, if we specify r first, it's actually a little bit easier. The smallest value of r is 1, and the largest value is 2. And then depending on what value of r you have different possibilities for z. You would have 1 less equal to r less equal to 2. And now what would z? Well, if r equals 1, how far can you go for z? If r equals 1, we can go from minus root 3 all the way up to root 6. If r equals 2, only one value of z works, 0. The range of z is going to depend on r. The smaller r is, the more possibilities for z will have. The larger r is, the less. So now I specify how far I want to walk out, and now I'm just going up and down. So this is drawing a triangle the other way. Now I have my circle. Here are my things of radius 1. And now, if I choose something of size r, I just see how high can I push that and still be inside the sphere. Okay. So if this is r, I just want to, how high can I lift that and still be good? If I lift it too high, the point is no longer there. And so for this given value of r, I see how high I can go up and down. Okay. So what is the hypotenuse going to be in this triangle? 2, always 2. The height is going to be my maximum value of z, and the base is going to be r. Oh, it's the same equation. So we get 2 squared is r squared plus z squared. So z is the square root of 4 minus r squared. And so z can go from negative square root of 4 minus r squared all the way to 4 minus r. So there's 2 different ways of writing down the equation in cylindrical form. Either way is fine. You can first specify z, and once you have z, that then tells you where r can go. Or you can specify r, and once you have r, then you have where z can go. It's kind of nice to specify r. I know r has to be at least 1, or I'm inside the green cylinder. And I know r can't be more than 2, so it's very natural to say r lives between 1 and 2. It's a little bit less natural to say 0 is between negative root 3 and root 3. You have to do a little bit of trick to find it. So I would say probably this is a slightly better choice. But we still have one candidate left. We have spherical coordinates. So for spherical, we have rho, p, and theta. I claim one of them is going to be very easy to figure out. Is it rho? Is it p? Is it theta? It's theta. So what are the choices for theta? 0 to 2 pi. So we know 0 is less equal to theta less equal to 2 pi. The hard part is figuring out the other two. So you can view this as I have a rocket ship. If it's pointing straight up, is it going to hit anything in the sphere that we remove the middle cylinder? Or does it just escape without hitting the It's escape. What if I point it at 90 degrees? Will it hit the sphere? No, it'll hit it in that whole stretch over here. So it makes sense that as I change the angle, there'll be a bunch of angles for C where it escapes without hitting anything else. And then we'll have a whole stretch of angles where it's going to start getting all these points here and some on the other side. So there's going to be a critical angle where we first hit the sphere. And if we call this Q0, and as we're coming down, this is 1, this is 2, this is Z. Oh, we've seen this before. Right? It's the same triangle. So we get again, Q0 is pi over 6. So at pi over 6, we just start hitting the sphere. As we go all the way down to pi over 2, we're still hitting the sphere. How far can we go before we no longer hit the sphere? So when do we leave? Yeah, pi minus pi over 6. So we have pi over 6 less equal to 2 less equal to 5 pi over 6. And as long as my angle is between those, I'm going to hit them. So now I choose some angle, and now this whole stretch of road will be permissible. All right, let me try to write what's going on. Okay. I think I've drawn enough angles. So here is some angle C. This distance over here is 1. This whole hypotenuse is 2. And now I want to figure out what values of rho can I take. So clearly, rho is at most 2. I have to figure out what is the lower bound for rho. Well, the lower bound is going to be where this hits the cylinder. We know we can move over one whole unit, right, because that's the radius of the cylinder. So we have a triangle. If this is rho, the small value, this is 1, this is P. Oh, okay, we got the sine of P equals 1 over rho. So rho is 1 over sine of P. And that's the final equation. I think the cylindrical coordinates is a little bit nicer here than the spherical coordinates. Even though you have points on the sphere, in the sphere, it's a cylinder that's going to be moved. And I think it's a little bit cleaner to write this in cylindrical. It's always worthwhile to test. Can you check your work? Are there anything you can do? Well, if my angle phi is pi over 2, then rho should run from 1 to 2. So if phi equals pi over 2, does rho go from 1 to 2? What's the sign of pi over 2? 1. Yes. And then if rho equals pi over 6, I'm sorry, phi equals pi over 6, does rho go from 3 to 3? I'm sorry, from 2 to 2. Because if we take the critical angle right here, pi over 6, there's only one value of rho that works. Over here, I can take any more from here to here. This is the best. I can go from here to here from 1 to 2. If I'm at this critical angle of pi over 6, there should only be one value of rho that works. Right? What's the sign of pi over 6? 1/2. Oh, good. If I put in 1/2, 1 over 1/2 is 2. And it reduces to 2 less equal to rho less equal to 2. It works there as well. Instead of writing 1 over sine t, what should I write? Instead of doing 1 over sine theta,
Oh,
I could do cosecant. If I see cosecant, what do I immediately do in my mind? I convert it to 1 over 1. I see no point in converting to cosecant if I'm going to then immediately in my mind convert back to 1 over sine. So I don't really process secant and cosecant well. I process sine and cosine well. I'm going to leave it like that. This is a good place to stop. Have a good